Go, Java, and Rust all have very different approaches to how they manage memory, which can have a huge impact on program performance. And there are two things that we mostly care about here. One is speed, how fast your program can do computations, which is roughly measured in the number of CPU cycles required to get the job done. The other is memory usage, that is, how much memory, usually RAM, the program needs to store its data, or your program's variables, while it does those computations. In languages like C, Rust, or Zig, memory management is effectively manual. You as the developer explicitly allocate memory by writing code that says, hey, this chunk of memory will store this data. And later, your code signals that it's done using that memory so that it can be freed up and used by other programs. In Java, things are different. Java's garbage collected, which means that memory management is automated. In Java, it's handled by the Java Virtual Machine, or JVM. When you run a Java program, you're actually starting up a virtual machine that executes your Java program's compiled bytecode. The JVM is responsible for allocating and freeing memory on the fly as it's needed. But this automation does introduce some overhead, and Java programs often use more memory than equivalent programs or similar programs written in languages like C. Now, Go falls into an interesting middle ground. Like Java, Go's garbage collected, so memory management is automated. But unlike Java, Go does not use a virtual machine. When you compile Go code, you get a single natively compiled binary just like you would with Rust or C. The difference is that this Go binary includes a runtime. It has an extra bundle of code that is compiled into every single Go executable. This runtime is what handles the garbage collection, other features like Go routine scheduling. One important aspect of Go's memory management is that it's often able to allocate more data on the stack than a language like Java does. And stack allocations, when possible, are more performant than heap allocations. So as a very generic rule of thumb, Go programs tend to use less memory than Java or C# programs, but because Go is still garbage collected, it does tend to use more memory than programs written in C or Rust.
So in many programming languages, characters of strings are actually called characters or chars for short. For example, if you iterate over a string hello world, you retrieve each individual character per iteration. But in Golang, these characters are not called characters or chars, they are actually called runes. That's why in this video we are going to clarify what these runes actually are and what the fundamental difference between characters and runes is. So let's go. So first, rune is a really special data type in Golang, and it is just an alias for int32. And basically everything that is an int32 can be automatically also a rune. So that basically means that the rune is equivalent to all int32s in any way or in all ways. And these aliases or runes are actually there to kind of be distinguishable from the int32s, right? Kind of makes sense. But in the end, they are just type aliases. And these runes are designed to represent Unicode code points. Now I'm going to show you what that actually means in a minute here. But let's just quickly first define a rune. Let's just say var r and then rune. This way we declare a rune. And then we just insert a Unicode code point or some sort of character or rune into these single quotes here. Right? And if we just look at the definition of a rune, we see here that rune is just a type alias, right? It is just in the end an int32. Okay, let's quickly clarify here why and when would you ever use runes in Golang. Well, runes are especially important when you deal with non-English text, right? Or really special characters like emojis or the Chinese language, Mandarin for instance. And runes really come into play and are essential for displaying these kind of really special symbols. And also these runes can be used to really handle text in a really efficient and optimized way in Golang. So in the end, they are optimized for Unicode character encoding. So that basically means that we can represent any sort of character inside of a rune, right? That is kind of representable with these Unicode code points. So let's just have a really quick example here. Let's just create a string, which we call s, for instance, right? We can do it this way, but we can also do it the short way. And then we just define some really special characters, like these two characters that are often represented in the German language, for instance. But we can also just add an emoji here. Just add the rocket here, for instance, right? So these three characters are really special, and we want to kind of handle them or kind of process them in any way. How can we actually achieve this? Well, we can use runes, right? So first, how can we define or kind of transform this string into a slice of runes? It's quite simple. We can just say r and then initialize it with the slice rune, and then we just use s here as a value. Right, and now R basically contains all the characters, all the runes or Unicode code points that S has. Right? I hope that makes sense. So now let's quickly print line maybe the original string and then the rune here. And if we run this code now, we do get the original string and then we actually get the Unicode code points of these characters. Right? And obviously it should be quite clear that also the spaces are characters. Right, so for instance, the character between the weird looking A and the rocket symbol is a space, and therefore it is represented as a 32. And as you can see, the rocket has a huge Unicode code point in this case. What we can also do, besides just printing it, we can also iterate over the individual characters of a string by just saying this here, right, range S, and then R is automatically a rune. If we just remove the slice, obviously, R is just a rune, right? So the individual character or Unicode code point of the string. So let's just print this here. Right? And if we just run this program again, we should actually see the index and then the individual rune, right? Which is quite cool. And it obviously also prints the rocket symbol, which is really neat. And we can do a lot of stuff with these runes, and you automatically also do a lot of stuff when you kind of do a lot of text processing or iterate over strings automatically. So let's just quickly clarify here what the actual difference between characters and runes is in Golang, and there is obviously a fundamental difference. Now, characters in general are just symbols, right? And runes are really Unicode code points, which are really similar to simple characters or symbols, but they have a specific focus on Unicode encoding. Now, when would you use runes in Golang? For instance, a really common use case would be text processing, or everything where you have to deal with text, right? So for instance, text analysis could be a use case where you kind of analyze each individual character individually. Now, and when it comes to text analysis, especially for like internationalization, right, where you have to handle a lot of different languages, where you also have a lot of different symbols. For instance, if you use the Asian languages, then really handling these unique runes is especially important. So let's quickly look at a real-world use case here. So let's get just rid of this example program, and then we can just start with a really simple text analyzer here. So let's just make a struct for that. Right, let's just say type text analyzer and then struct. And then for instance, let's just say that we want to measure the word count. We maybe also want to measure the line count and the character count, right? Or the rune count. But maybe also like the uppercase letters, right? We also want to kind of count the uppercase letters, but also maybe the lowercase letters. So we just call this upper and lower count. And these are the things or the statistics we want to analyze, right? Or kind of retrieve from a simple text that could be written in any language. Alright, so let's quickly just say type text analyzer and then struct. And then for instance, let's just say that we want to measure the word count. We maybe also want to measure the line count and the character count, right? Or the rune count. But maybe also like the uppercase letters, right? We also want to kind of count the uppercase letters, but also maybe the lowercase letters. So we just call this upper and lower count. And these are the things or the statistics we want to analyze, right? Or kind of retrieve from a simple text that could be written in any language. Alright, so let's quickly create our new text analyzer function here, and in the end this should return a pointer to text analyzer, and then we just return a new text analyzer struct, which for now is just empty, right? And in the end these kind of 5 struct fields are also kind of 0 or empty in this case. Alright, let's just create, I think, the most basic function, which is just a print function, right? So we say TA and then text analyzer, and then we say print stats, for instance. Now I'm not going to really focus on the visibility here of this kind of struct, right? In this case. Alright, let's just create, I think, the most basic function, which is just a print function, right? So we say TA and then text analyzer, and then we say print stats, for instance. Now I'm not going to really focus on the visibility here of this kind of struct, right? Because obviously it's not important for me right now, because this struct and these functions will only live in our main file, right? So I'm not going to focus on the visibility here. And in the print stats function, we are just printing this statistic. So basically every single field, every single struct field we've defined here. So let's quickly do this here, right? So what we do are kind of 5 printfs, and here we just print the individual struct fields, like I said before, right? Nothing really special going on here. And then let's just use this text analyzer in our main function. Now what I have here is a really simplified text that we want to analyze, right? So we have emojis, special characters, new lines, and all sorts of characters. Now let's just say A, and then we initialize a new text analyzer, and then we say a print stats, and before that we say a.analyze, and in here we pass in text, right? Now obviously we have to create this function, so let's quickly do this. And this is obviously the core of our analyzer. So here we obviously say the pointer to text analyzer, because we want in the end to manipulate the struct fields, right? Because if we do not do this, the struct fields can be manipulated, but in the end they are not manipulated, right? Because we kind of copy here the struct by value and not by reference. So let's just do this and then say analyze, and then this function takes in a text string and doesn't return anything. So let's fill in the line count and character count here, because that should be really simple. Now you might assume that we could use the length, right, of the text, but this is not the case. And this is really important to understand here. Now why not using length, right, the length function, is because strings are UTF-8 encoded, and thus not all characters take up the same number of bytes. So for instance, a character like A takes 1 byte, whereas a character like emoji, for instance, takes 4 bytes in UTF-8, whereas a character like emoji, for instance, takes 4 bytes in UTF-8. And this function len or length just gives us an inaccurate result or inaccurate length when it comes to this Unicode text, right? And this is really important to understand, especially when you have to deal with multi-byte characters, for instance like emojis. Now let's just make an example here, right? Let's just create a slice of runes quickly, and then we just iterate over our rune slice. Let's just rename R to runes here. And then we transform R to a string, right? Why we're doing this is just to kind of demonstrate what the actual byte length of a character is, right? And then we say byte count and we initialize it with the value rune length, and then we say R. And then we will just add a printf statement where we kind of print the rune itself, the UTF-8 version of our string, of our currently iterated rune, right, we convert it to a string with this line here, and then the byte count for our rune itself. So let's quickly start this program here. And what we can actually see with the first 3 lines is the UTF-8 representation, but then also the bytes or the used bytes, right? So we can actually see that the rune A itself has 1 byte. The next character, which is a special character, has 2 bytes, and the rocket emoji has 4 bytes. Right, so in the end it is really important to make use of